Hello again. As Eric said, I'm going to talk about a multi-rotor system based on vertical axis turbines. If somebody had told me, maybe even only 5 years ago, let alone 10 years ago, that I would be talking on such a subject, I would have been flabbergasted. I had some thoughts about this in the middle of last summer, and a team got together and started to look at it. We presented a paper, a joint paper at the Wind Europe conference in Bilbao. And I'm leaning on the work there, but also some additional angles. So why use vertical axis turbines? So in order to explain that, I'm going to tell you what's wrong with vertical axis turbines. If you take the standard H type of vertical axis turbine, because the blades cannot present the same angle of attack and attitude to the wind in a cycle of rotation, it cannot operate consistently at the highest lift-to-drag ratio of the airfoils. It's effectively more draggy, therefore the optimum speed is lower. It's around 40-45 meters per second, half or less than half of what some of the horizontal axis turbines may run at. So you have double the torque or more for the same power, which is unpleasant for drivetrain weight and cost. And you have less power for the same swept area. If you move from what I've called the standard H-type to a high aspect ratio vought, then by shrinking the diameter and exploiting the fact that the swept area is a rectangle and not a circle, you've got 2 degrees of freedom there. Shrinking the diameter, you get a faster shaft speed at whatever your tip speed is, 40 meters per second. You can solve the torque problem. Also, because of the high aspect ratio of the blades, the different tip loss mechanisms, but a way to think about it simply is that the tip loss is much reduced. So this high aspect ratio of is wonderful, except for one thing. It's a very long cantilevered structure and pretty problematic as a single rotor, especially if you wanted to upscale it. If you look at the spiral bladed vought, another variation, at small scale that's very nice. The double curvature of the blades stiffens the structure, but you can imagine that it would be problematic to upscale, and it doesn't address some of the other issues I've mentioned. So having said all that, I'm further away than I started in answering the question, why vertical axis? I'll give you the answer and then I'll try and justify it. Almost all these problems of the single rotor system can be solved in the multi-rotor configuration. So first of all, before directly explaining that, just give you a vision of the kind of system we were considering. A 48 megawatt multi-rotor system using 96 500 kilowatt vertical axis turbines. I've presented this image on the right before, which was a hastily constructed sketch for the Bilbao And it gives a false impression of how dense the area is with material. The little extract on the left shows the structural members in true proportions. The red rectangle is open, so that we have 4 vots side by side in that space. And the reinforced structural members are all at the back of the frame. So let me just, what are these synergies? Well, first of all, the high aspect ratio avoids tip loss. We've heard about blockage effects, and in the presentation from Angus, you perhaps noticed that they look to be stronger than for horizontal axis turbines. Because we're adopting this high aspect ratio design, the shaft torque problem is solved. The support structure problem is solved because it's nicely integrated with the frame, and now we have a vertical axis turbine where you have top and bottom bearings. To avoid compression and buckling sensitivity, you can hang the turbine on the top bearing and have more of a locating bearing at the bottom. If you connect them vertically in a column, not only do you reduce the number of generators, but you can set them at different phase angles and in effect have an 8-bladed turbine without, in fact, having the complexity of a single turbine of that sort. It's a simpler turbine, and there's obviously no local yaw system, and we choose to avoid pitch systems, and come to the implications of that a bit later. And in terms of environment, I'll indicate that it can potentially satisfy all of reduce, reuse, and recycle. So 4 rotors connected together, I've mentioned, and the phase difference. Shaft brake on every rotor, sufficient capacity that the system's safe from overspeed in the event of failure of 1 or 2 brakes. The essential control method is by generator reaction torque, inducing stall in the rotors. That's variable speed stall, essentially. This type of control could be questionable for single turbines in terms of power quality. It's not that it hasn't ever been done on horizontals, it has. But in the combined output here, we have the average of 24 independent generators. So the key result is that most of the problems of a single vertical axis turbine are solved in the multi-rotor configuration. This is some preliminary work from Carlos, who will be speaking shortly. And basically, you maybe get about 8% tip loss on a 3-bladed rotor. So CP could go from something like 0.5 to 0.54 if you could wipe out tip loss. Here, you're upping the potential P of the VOT by this high aspect ratio. Angus has talked a fair amount about blockage, and Carlos will have more to say on some of the effects here. I'm just summarizing. It looks to be a stronger effect with the verticals. We don't know what's going on with a mass of verticals like that, but that's being explored in Angus's PhD. There's some evidence from the literature that the wakes could be diverted upwards. If that happens, you get recovery from the free flow above the turbines, and this would allow much denser wind farms, and Carlos, I know, is going to talk a lot about that. Sven is the world's leading expert on support structures for multi-rotors. He's been working with Peter Dahlhoff for a while, and he very quickly developed this structure. The main point making about it is that the optimal design has a mass of different tube sizes. You can reduce several hundred tube sizes to about 20 standard sizes with only an 8% weight penalty. I've talked before about the manufacturing aspects of and benefits, if you like, of multi-rotor systems. But I'll just highlight that if you have a constant section blade, and move on to, no, just one moment. I'll stick with this. If you have a constant section blade, Mark could probably say even more, but for example, it's not out of court to be using a material like aluminium, which is a bit energy intensive to make, but the constant sections would be very reusable in other structures, and it's almost totally recyclable. I understand that about 80% of the total aluminium production in world history is still in circulation. Now we come to O&M. The people who have done the real work in this have already been talking, and I would say if you have any questions about it, you'd be better to address them to Jade and Abdullah rather than me. But the trend we're seeing with the simplification of the VOTs is very favorable. The black line there is availability decreasing with other types of designs. It probably is a bit extreme for the multi-rotor horizontal for various reasons that a lot of features weren't modeled. But on the subject of O&M, I maybe want to sort of plant a picture in your head that a single large turbine experiences severe failure in winter, a major failure in winter, a floating turbine. So you've heard the story about Kincardine in relatively benign conditions. With the multi-rotor system, you can allow maybe 10% of your turbines to fail. You don't need to do anything. If they're overrated, you can work some of the other a bit harder and recover the power and so on. I envisaged that you would centralize all the electronic and control equipment in a room at base level that was air conditioned and with backup for the humidity control and so on. And with automatic switching of spare converter units and controllers to mitigate possible loss of availability. So this VOT idea is at a very early stage. We need to look at the drivetrain a lot more. The O&M issues are very promising. Yeah, that's mentioned. Large benefits to the environment common to all multi-rotor systems, but maybe even more so. So that's it. Thank you.